exponential functions and their integrals. So all I did was kind of try to pick weird problems, like E problems, LN problems, like all the ones that I think you're saying are kind of tripping you up. So I looked for all of the goofy, like, U sub problems and said, okay, let's look at them. So the most basic rule for the derivative of an exponential function is e to the u. So antiderivative of e to the x is e to the x plus c. We know that. So what happens though when that x value is something other than x? So what happens when we have e to the 5x? So these are where the u substitution starts to come into play. So we've already looked at a couple like this. Your idea would be that you make u 5x, du becomes 5 dx. We're missing our 5, so we divide it out. So that gives a 1/5 in front. Integral of e to the u du. 1/5 e to the u plus c for our rule. And then plug back in our u. The big key point and difference of yesterday's lesson to today, back to no bounds. So knowing the difference between bounded versus unbounded, if it's unbounded, you're going to have that plus c. You want to make sure we always include that for unbounded trig functions. If you have e in your problem and it's a u sub, you are always going to make whatever the e is raised to your u value. So in this case, our u value is going to be sine theta. Du is cosine theta. D theta. Therefore, we're integrating e to the u du, giving us e to the sine theta plus c. So as I previously mentioned, anytime we have an e, our u is typically going to be the e's exponent. So sometimes we see this and then we see our square root and we see the e, and it starts to make us question which one becomes the u. So again, if you have an e, the u is going to be the exponent, regardless of, in this case, that square root. What happens, or makes this problem really nice, is e to the u is our square root. The derivative of the square root is 1/2 x to the negative 1/2 dx. But if you think about anything being raised to the negative exponent, that drops it down to that denominator. What I don't see in my problem is the 1/2, so I'm going to multiply that to the du. But this becomes 1/, square root of x dx. So I end up seeing that right here in my problem, because technically there's always that 1 in the numerator. So we're going to end up integrating to e to the u du. Are we okay with that manipulation? Kind of see what I did? So then you get 2 e to the u plus c, or 2 e to the square root of x plus c. So this one's a little trickier, right? You have an ln of x, you have a 3x in your denominator, And you're kind of looking at it and going like, well, I don't know a rule for integrating ln, so I guess that's what my u value is. Like that's kind of like I think the thought process that we would go through. And that's the thought process I would try to hope that you would go to. So we don't have an integration rule for ln. So if you have an ln in your problem, the whole ln is going to be your u value. So if you have an ln in your problem, that ln is going to become my u. What works out really nicely in this case is the derivative of ln is 1 over x. So when you substituted, the ln became your u, and then the 1 over x dx becomes your du. So that 3 is sort of hanging out, tagging along, but remember we know we can take out constants. So I'm going to take that 1/3 and pull it out in front. Now, what's an antiderivative of u? Well, it's our most basic rule. So the antiderivative of u is u squared over 2. Add 1, divide by your new one. No bounds again, so plus c. So you get 1/6, replacing u back with ln. I get 1/6 ln of x, whole quantity squared, not just the x. So that's really important, is making sure that you have all of the ln of x being squared, but not the 6, plus c. So you can't break this problem up, right? If you have a single denominator, you should always rewrite it under every numerator term. But if you have a denominator that has something being added or subtracted, I can't break this up into fractions. So I always kind of said, if you had an e to a crazy exponent, you made the u value the exponent. But is that an e to a weird exponent? No. So now, what are our thoughts? Like, what do we think? Yeah. Perfect. And that's exactly what I'm going to do. Because if we make the entire denominator the u value, then my du becomes the numerator. Because derivative of e to the x is e to the x. Derivative of 1 is 0. So if you get stuck, you're trying to find a way to make your problem easier, right? So now e to the x dx becomes du. The denominator becomes u. And I end up with 1 over u du, which is really just, natural log, ln. So the only thing that's unique about the ln now, that we didn't worry about so much before, is that if you take the natural log and it has the u subs in it, you have to put absolute values around everything. Because what happens is now you have a function and a function, and we don't know what the values of it could be. So sometimes you need the absolute value those problems. So you have the natural log of absolute value e to the x plus 1 plus c. So is this kind of helping like the weird ones? Like is this making you feel like, okay, I can do some of those funky looking u problems now? Because they are, they're just different. Like what makes the u sub like hard is that there's not always a set pattern. And then yesterday we talked about the a value. So this is like an e to the u, but the ln in the e to the u fizzles away, this one needs to include the ln with that 5. So my u value is 2x, my du is 2dx, dividing over that 2. So I end up with 1/2 5 to the u du. And then I just need to remember that this is my a to the u rule. So like e to the u, it stays a to the u. However, we have to also then divide by ln a. So in this case, we're also going to divide by ln 5. Whoa, plus c. And then just substituting back in, we get 1 times 5 to the 2x over 2 ln of 5 plus c. And then just because I like your u bounded problems, the u is pi t. I don't know why I like saying that, but I do. Du is pi dt. We need that pi on the other side. And then changing my bounds. U of 0, u of 1. So I get 1 over pi 0 to pi of e to the u du. So 1 over pi e to the pi minus e to the 0. Now don't goof that up. Anything to the 0 power is
No events go. Please report to the office. No events go.
so we get 1 over pi e to the pi minus 1 over pi. So again, very, very similar. So what's my u value going to be? Yep. Do I know the ln of 1? 0. Ln of e is 1. Because they're inverses of each other. So they'll cancel and become 1. So my new bounds are 0 to 1 of u du. So again, following carefully, making sure we get that notation. Changing our bounds, u, du, you need the variable and the variable of integration. Then once you take that derivative, writing it, putting the bar at the end that says I'm evaluating from blank to blank, making sure it's always top on top, bottom on bottom. Then the next line is plugging in. We get 1/2. Okay, and then that last one, anything where your e is kind of hanging out by itself, so my u is going to be that x squared plus 1, du is 2x dx, the 2 is not needed, so we pull it out in front, so I have the 1/2 here, I'm going to change my bounds, e becomes to the u, x dx becomes du, so then I need u of 2 and u of -1. So my bounds become 2 to 5. Anti-derive. Unless it was a calculator question and you needed to like round to 3 decimals, that's your answer. Okay? So that means